Hi, I'm John Thompson. I'm a senior product manager in the IoT software team here at ARM, and I'm joined today by Sam Brugan, product manager for IoT. It's a pleasure to be here with you today to provide an update on our SystemReady program, specifically the SystemReady IoT band, the work that we've been doing to support the Yocto project, and how to deploy Yocto Linux on SystemReady IR compliant hardware. In IoT, the embedded edge has a crucial role in supporting a diverse set of use cases with a range of power and performance requirements. Traditionally, the IoT deployment model has been to generate data through sensors and endpoints in large volume at the edge and process and act on that data in the cloud. But as we scale to trillions of connected devices at the edge, that model won't always be feasible because of the sheer amount of data being generated and needing to be moved, and an infrastructure that is unable to scale at the same pace. To deliver reliable services at scale, we must be able to process more of this data and host intelligence at the edge. And to do this, we have to embrace cloud-native software principles, enabling distributed compute models from the cloud all the way to the endpoints. To address this, we announced Project Cassini in 2019. Project Cassini is an industry-wide initiative that addresses two major barriers to deployment in IoT: scalability and fragmentation. Project Cassini enables the migration of workloads from the cloud closer to the data at the edge, while creating a consistent, homogeneous deployment model for end applications, making it simpler to scale solutions across a diverse set of devices that just works. To achieve this, there are three pillars of the project. There's the ecosystem pillar, which provides a set of edge solutions reference implementations. The security pillar, which includes PSA, which was developed to meet the need for standardized security across the IoT industry, and Parsec, which provides an abstraction to various roots of trust, allowing applications to maintain their portability while enabling the highest level of security available in a system. Parsec exposes a common security API for application developers and is available in multiple languages. And as of the hard-not release of Yocto this year, MetaParsec is now provided as a sublayer of the Meta security layer, making it even simpler to deploy and to use. And then, of course, we have the standards pillar, which includes a set of hardware and firmware specifications, which Sam will go into a bit more detail on shortly, and the SystemReady certification program. The goal of SystemReady is simple. It enables the operating system to land on the broad ecosystem of ARM hardware. It provides the confidence that software just works on ARM-based devices out of the box. This is what we're focusing on today. With SystemReady, we're focusing on the common components of the software stack: the operating system, the hypervisor, and middleware components, so that these just work, enabling our partners to focus on innovating and deploying the differentiating application layers of software. To do this, we're focusing on establishing a more uniform hardware system architecture and consistency around key processes like boot through a set of standards, hardware requirements, firmware requirements, and architectural compliance suites, which results in a simplified and faster time to market for our partners. Of course, when it comes to standardization, there's a balancing act. If we have too much standardization in the ecosystem, then partners will find it difficult to develop the new purpose-built solutions that work for them. If there's too little standardization, we run the risk of having low value, same but different variability that injects cost into the software ecosystem for no real benefit. With SystemReady, we aim to strike the right balance, enabling innovation while still providing flexibility and reducing barriers to deployment in IoT, lowering the cost of software deployment and maintenance. To talk a little more about SystemReady, how it's relevant to the Yocto project, and how we're enabling Yocto Linux deployments on SystemReady IR platforms, I'd like to introduce you to Sam Brugan, one of the product managers in the ARM IoT business. Over to you, Sam.
So here I'd like to discuss SystemReady IR in a bit more detail. SystemReady IR is targeted at embedded and IoT platforms, and the ultimate goal of SystemReady IR is to address the fragmentation seen within the IoT world, bringing a level of standardization to both firmware and hardware, which will give developers a consistent set of interfaces on which they can rely on. So here I'll briefly take you through the DNA of a SystemReady IR compliant platform. Firstly, SystemReady IR platforms are built around the UEFI specification, which defines the boot and runtime services expected by an OS or hypervisor. Platforms also take advantage of the device tree specification. Device trees are a hardware description format, which the OS kernel can use to understand the hardware components it's working with. These platforms will of course be ARM-based and can be either 32 or 64-bit and will run Linux of some flavor. Example supported distributions include Fedora and Ubuntu, but most importantly for this discussion, Yocto. And then as you can see below, we have a range of other OSs under investigation too. Hardware specification is covered by the ARM base standard architecture, and firmware is covered by the embedded base boot requirements specification. On this slide, I will discuss the specific requirements that a platform must meet in order to be certified as SystemReady IR compliant. To validate that a platform meets the relevant requirements, we have developed the architecture test suites for each SystemReady band. Vendors can then run this test suite on their platform, and this will provide an output report which will tell them whether or not their platform has met the benchmark for certification. So firstly, hardware. As previously mentioned, SystemReady IR hardware requirements are described by the BSA specification. BSA offers a standard hardware architecture for SoC designs to work to. It specifies a 64-bit hardware system based on the ARM architecture, and there is no 32-bit BSA specification. So this section only applies to 64-bit systems. BSA includes baseline requirements covering processing elements, memory subsystems, interrupts, memory management units, and other power and security features. And basically, BSA describes the minimum set of features for an OS to boot and run. Further requirements can be added on top of these specifications for specific market requirements. For instance, there's a server-based standard architecture, which adds in additional requirements. However, for IoT, which we're talking about today, the baseline BSA specification is sufficient. However, for SystemReady certification, BSA compliance is not actually required at this point. It's only necessary to provide the test logs from the test suite for informational reporting purposes. And for 32-bit systems, of course, there will be no test as there is no 32-bit BSA specification, as I mentioned before. We implement this reporting requirement to improve awareness of the standards and to try and nudge vendors in the right direction for hardware standardization, but without making the requirements for SystemReady certification too exclusive at this point in time. On the firmware side, compliance with the embedded base boot requirements is required. EBBR defines features at the interface between firmware and an operating system or hypervisor. Compliant platforms present a consistent firmware interface to the OS, allowing compliant OSs to boot unmodified and to employ advanced features such as secure boot and firmware updates. EBBR achieves this by leveraging the UEFI specification to define the boot and runtime services expected by an OS or hypervisor. And then finally, we require that platforms implement the device tree format for hardware description. Traditionally, hardware descriptions were baked into the OS kernel, requiring forks for each hardware target. The device tree format allows us to decouple the hardware description from the kernel binary, which helps us to reduce the number of OS forks that we require. So that covers the specification that compliant platforms must meet. But then the final requirement for certification is that vendors must provide OS installation logs for 2 separate Linux distros to prove that everything works as intended. Devices that meet these requirements can then be certified as SystemReady compliant, and you can identify these with the nice orange badge you can see here in the center of the screen. So far, we have 2 NXP IMX8 based boards certified, with more boards in the pipeline. And the plan is to build up a diverse ecosystem of SystemReady IR compliant boards for you to choose from. So Now, I think it's important to briefly introduce Yocto. I'm sure a lot of you are very aware of how it works, but I think it's good to establish a baseline level of understanding. So let's just take a minute to do that. Firstly, an important point that the Yocto projects themselves are keen to emphasize is that Yocto isn't a Linux distribution, rather it's a tool that helps you build one. It consists of three main components. These are a set of tools for Linux development, the Open Embedded Build System, and finally Pocky, which is a reference embedded distribution. Pocky combines core components from the Yocto project and is well tested and supported, receiving frequent updates. Developers can use this reference distro as a foundation and adapt it to meet their requirements, or they can simply use it as a guide for building their own distros. A key feature of Yocto is that it employs a layer model in which functionality is logically organized into layers, creating a level of modularity. Layers group together related recipes and effectively tell the build system what to make. These layers can either be custom made or they can be found in online repositories, such as the Yocto Project Layer Index, which is an index which curates layers that have been tested to work well. A project could include board support package or BSP layers, a Pocky layer, and of course, layers that implement functionality relevant for that specific build. Once you've completed your layer hierarchy, then the Open Embedded Build System uses the bitbake tool to parse the recipes and compile a bootable image. And at that point, you're done. So Yocto is highly popular with embedded developers because it allows them to easily build custom images that optimize speed, footprint, and memory utilization. So I've just given you a super high level intro, but if you want to learn more about Yocto, I'd encourage you to go onto the Yocto Project's website and read the official documentation. So moving on, let's discuss why SystemReady IR and Yocto are a winning combination. So Yocto is the tool of choice for many embedded developers. These developers tend to have to support a large variety of hardware, meaning that porting software becomes a mammoth task. To get OSs to boot, one often has to make specific modifications to the software for each specific hardware target. The result is numerous software forks, which quickly spirals out of control to become a maintenance nightmare. But platform enablement is expensive and time-consuming. These resources and effort could much be better spent on differentiating features, the features that will actually add value. So with SystemReady, we're actually trying to address this. The key output of SystemReady IR is that compliant platforms expose a consistent set of interfaces. This means that developers can rely on these when porting software. They can trust that if they drop their distro on new compliant hardware, it will boot without modifications. The result is a software experience that just works. Developers can scale software across larger deployments, and they can also devote more of their valuable time to creating value-add features. Another nice benefit is that it enables a more streamlined development flow. As I mentioned earlier, there are other SystemReady bands covering different use cases, and software is portable across all of these bands. So to provide a nice example of how SystemReady enables a nice development flow, one could develop their Yocto build on a SystemReady SR compliant server and then deploy it seamlessly to a SystemReady IR compliant embedded board. So hopefully by now it's clear the value that SystemReady is able to provide to the embedded developer. So now I'd like to show you a demo. This will demonstrate the process of getting a Yocto build up and running on a SystemReady IR certified board. In this case, an NXP IMX8 8M Mini evaluation kit. This should help to illustrate how simple this process can be. This talk is accompanied by a more in-depth guide, which you can follow if you want to recreate this yourself. We'll provide the link in the description. Okay, let's begin the demo. So the first thing we need to do is head over to NXP's website for the Embedded Linux for IMX Processors page, go to the Releases tab, and download the SystemReady boot image for the board we're working with. Accept the license agreement and download the file. Then we need to head over to NXP's GitHub after we've completed the download. So yep, head over to NXP's GitHub, then to the MFG Tools repository. Head over to the latest release and download the Universal Update Utility tool. This is the tool that we'll use to flash our board. Then finally, make sure you go to the Yocto Quick Start Guide and install all the tools that you need on your system to make sure the Yocto builds without any errors. The next thing we'll need to do is make sure the board is configured correctly. So you need to take the switches on the board and configure them as shown here. So they put the board into download mode. This allows you to flash the eMMC memory. You'll also need to connect the USB-C power cable and connect to the USB-C programming port to your computer, and also connect the micro USB cable to your computer for the serial port. Make sure your board is switched off while you're doing this. Now the board is set up properly, we can move back to our terminal. You can see we've already downloaded and unpacked our files. Now we will run the UUU command, telling it to flash the eMMC memory with the file that we've recently downloaded. That is the SystemReady firmware from NXP. When you run the command and we power on our board, it will automatically start flashing the boot firmware. As part of this process, it will install a version of U-boot that is compatible with SystemReady. Turn the board back off, then return the switches to their previous positions for eMMC mode. Once this is complete, the device will be ready to boot SystemReady compatible operating systems. Now the board is set up correctly, the next step is to set up Yocto. And the first thing we need to do is use Git to clone the Pocky repository onto our build host. As I mentioned, Pocky is the reference distribution of the Yocto project, and we'll make use of it for this demo. Once Pocky is downloaded, we next need to clone the meta-ARM Yocto layer to our working repository. This layer provides all the recipes and tools needed for ARM platforms, as well as containing generic and QEMU machines. Next, we need to move to the Pocky directory and use the OE in its build environment setup script. This script sources the build environment to this directory and creates a local configuration file named local.conf. Now we need to add the two meta-ARM layers that we need for this demo to the configuration file. We have meta-ARM toolchain, and then we have meta-ARM itself. And we can add these using the bitbake layers add layer command. Once we've added our layers, we'll need to edit the configuration file to change the machine type parameter. So we'll scroll down. Here's the machine type parameter, and we'll change this to generic ARM64 as we are working with a 64-bit ARM-based system. Now we'll move to the bottom of the file, and we will add a couple of configuration items. So what we want to do here is we want to set up systemd as our init manager, and that's because it's able to properly detect the console ports and so on. As well as this, we will also change this parameter right here, this following one, to make sure that we don't install systemv init, which is the default init manager. And then with that done, we can save this configuration file as seen. Okay, now we're ready to build Yocto. We'll do this by running the bitbake command, which builds the final Yocto image. This will take a little while to complete. And obviously we'll speed it up right here. So once Yocto is finished building, we can copy the image that we generated to a micro SD card using the DD tool. Once the image has been successfully copied to the SD card, we can now run sync to make sure that everything is written properly. And then we can eject the card from the system and insert it into our dev board. The last thing to do is connect to our dev board serial terminal, in this case using Minigon. And we power on the board. You can see here it's initializing. First, we see U-boot, and then we will see our systemd boot menu here. And now we're booting our Yocto image. And then eventually we will see a login shell for Yocto. There it is. And with that, we complete the demonstration. We've successfully built a Yocto image and deployed it on a SystemReady IR compliant board. So that is the end of the demo. So that completes this presentation. Thank you for joining us today. Hopefully the demonstration I just shown you is demonstrated just how straightforward it is to deploy Yocto on SystemReady IR compliant hardware. Please visit our website to download the supporting white paper, which goes into much more detail on SystemReady and on Yocto. And it also includes a step-by-step walkthrough to getting Yocto up and running. If you have any questions about anything that we've covered today, don't hesitate to contact either myself or John, and we'll be happy to give you more information. Have a great Dev Summit, and thank you for listening.